Hi, my name is Mark Otterson. Used to teach physics, and a lot of the students called me Mr. O, so that name sort of stuck. This is my first YouTube video. I'll be planning to make more, and I'm always open to suggestions as to how I might improve. This session is about kinematics, which is basically it's a series of mathematical equations that assume constant acceleration. The equations are only valid if acceleration is constant. Kind of important to notice that these particular equations, they don't deal with the forces that are causing the motion, or they don't worry about the mass of the object being accelerated. These are just math equations. In future courses, we will learn how to solve the same problems using Newton's laws of motion, where we worry about forces and masses. Again, these equations are only valid if there's constant acceleration. An example of acceleration would be when you hit the gas pedal on your car. For the first few seconds, you have constant acceleration. Or if you hit the brake pedal on your car, you'll go through a few seconds of constant deceleration, which is basically acceleration negative. It's in the opposite direction of your motion. So there's 5 variables that we're going to deal with: initial velocity, final velocity, acceleration, time, and displacement. The nomenclature in various textbooks can vary from this a little bit. Sometimes initial velocity is referred to as v sub I instead of v sub o, which is velocity at time equals 0. Sometimes time is referred to as delta t, basically the elapsed time during the period of acceleration. Delta x might be referred to as x. If we're talking about a vertical acceleration, we will generally use the variable y. X is horizontal, y is vertical. In these particular problems, one dimension, it doesn't matter, but at some point we'll be doing two-dimensional problems where you have to keep your x and your y separate. Projectile motion, where you have a two-dimensional problem. You have to keep your x and your y separate. Okay, there's 3 equations that contain the five variables. Let's take a look at these equations briefly. Notice that each equation, the way they're written, has initial velocity as the first term on the right side. The second term always contains acceleration. First term contains initial velocity, second term contains acceleration. So if your initial velocity is 0, for example, a car at a starting line or a runner at a starting line, that first term disappears and it simplifies the equation a little bit. Second term contains acceleration. If that were to be 0, you'd no longer have an acceleration problem, you'd have a constant velocity problem. And that third equation would just become displacement equals velocity times time. Or displacement, for those of you who aren't real familiar with it, it's just change in location. It's like distance, only distance is a scalar quantity, displacement is a vector quantity, and that'll make more sense here in a minute. If you know any 3 of the variables, you can always calculate the other 2. Just be aware that anytime you see a problem, they have to give you 3. 3 of the variables have to be provided, and any of the equations can be rearranged algebraically if you desire. For example, equation 1, which is VF equals VO plus AT, you could certainly rearrange that equation to put your unknown quantity on the left-hand side and have all your known variables on the right-hand side. Some teachers require you to do that before you plug the numbers in. Some teachers don't. Just whatever you prefer. It's important to mention that these equations involve vector quantities. Vector has direction and magnitude, as opposed a scalar only has magnitude, and that'll make sense here in a minute as well. And each one of these motion problems, you have to define which direction is positive, which direction is negative. If you have a race car going from left to right, you could define left to right as being a positive direction. Acceleration going in a positive direction would be a positive acceleration. Velocity in the positive direction would be a positive velocity. Displacement, if you end up in a, if you end up further right than where you started, that's a positive displacement. Just like up and down problems, if you're dropping a ball off of a bridge and you defined upward motion as being positive, then you're defining your downward velocity as being negative. Likewise, your downward acceleration is negative if it's being pulled in that negative direction, or your displacement would be a negative displacement if the object ends up lower than where it started. The length of the arrow represents magnitude. That doesn't come into play in these particular problems, but it will when you start doing some vector algebra in the future. Every vector can be shown as an arrow. The direction of the arrow represents the direction of the vector. The length of the arrow represents the magnitude of the vector. Okay, and I'm just going to give you a brief introduction to scalars and vectors. The scalar you're probably most familiar with would be distance. The corresponding vector quantity is displacement. The only difference between the two is that displacement is concerned with the direction of the displacement. You can talk about walking 50 feet, and that's fine. That's a distance. But if you talk about walking 50 feet in a particular direction, that's a vector. Speed is a scalar. Miles, 35 miles per hour. You're not concerned about the direction. That's a scalar. If you're talking about 35 miles per hour in a particular direction, that's referred to as a velocity. That makes it, instead of speed, it becomes a velocity vector. Acceleration can be a scalar or a vector. There is no different word for a scalar term. If you're worried about the direction, then you would use the acceleration, and you have to provide the direction of the acceleration. And again, acceleration is just change in velocity. Other examples of scalars would be time, temperature, and energy. There is no direction associated with those. And other examples of vectors would be force and momentum, which don't come into play in this particular session, but they will in future sessions. Force is simply a pull or a push on an object, and it has to be defined by both the magnitude of the force and the direction of the force. Momentum, likewise. Okay, let's do a few examples, and it'll hopefully example problems will help you to learn how to solve them. Let's see. First example: car is initially traveling 2 meters per second. Driver pushes down on the gas pedal, and 3 seconds later, he's going 14 meters per second. We're going to assume constant acceleration during this 3-second period, and that's enough information to calculate the rate of acceleration and the distance the car traveled, or we should probably refer to that as the displacement of the car. So I think it's always useful to draw a little picture of your problem. It helps you to visualize what it is you're trying to solve. So, and it doesn't have to be anything fancy. Just show the variables and show what you're trying to figure out. In this case, you got a guy in a race car traveling from left to right. So we're going to define that as a positive direction. So his initial velocity is a positive 2. Final velocity is a positive 14 because he's traveling in the positive direction. Our displacement is shown there as delta x. The displacement, the change in location of the car during that 3 seconds. I would always get in the habit of listing your variables in a systematic method. I would always put the variables I put them in the same order and just put down the values that you know. In this case, we know the +2, +14, and time equals 3 seconds. And I would list my equations. And so now the first step would be to figure out which equation has only one unknown variable. In this case, let's go with equation 1 because that's the simplest equation. And there's only one unknown variable. We can calculate acceleration. And again, you could have rearranged that equation before you plug your numbers in, or plug your numbers in first and then solve for A. Doesn't matter to me. Your teacher, some teachers require you to rearrange the letters before you plug the numbers in. And then now that you know the value for acceleration, you can use either of the other two equations to solve for delta x. In this case, I picked equation 3. Plug in your numbers and you get an answer. And I would say get in the habit, generally you only need the two equations to solve the problem. I would get in the habit of plugging my answers in the remaining equation. You can use equation 2, plug your answers in and verify that you got the right answers. It's a good way to check your work. Example 2, basically the same problem, only in this case, instead of giving the time, we're going to give the displacement. So he starts by going 2 meters per second. 20 meters down the road, he's going 14 meters per second, assuming constant acceleration. You have to assume that. Well, put it this way: those particular equations, kinematic equations, are only valid if you have constant acceleration. So we're going to assume that. We're going to calculate the rate of acceleration and the elapsed time. Again, let's draw a picture. You have your little guy in the race car going 2 meters per second. 20 meters down the road, he's going 14 meters per second. So that's your positive velocities and positive displacement, which is what you define. You define that particular direction as being positive. Again, I would list your variables systematically, write down what you know, the known quantities in a systematic manner, write down your equations, and then pick the equation that has only one unknown variable. And in this case, we're going to start with equation 2 and plug in your numbers. Again, you could rearrange that equation before you plug in the numbers if you desire. And determine that A is, in this case, A is equal to 4.8 meters per second. In other words, acceleration just means your velocity is increasing by 4.8 meters per second each second. That's why it's 4.8 meters per second squared. Now you plug that number in and you'll determine that it took them 2.5 seconds to go down, to go 20 meters at that constant acceleration. Okay. And again, I would go ahead and check my answer using the equation that you had not used before. So I'd plug my answers into equation 3 and it should come out. It should work. And if it doesn't, then you know you made a mistake somewhere. Okay, now we're going to do a couple free-falling object problems. Anytime a ball is flying through the air, it's a free-falling object. If you throw a ball straight up in the air, it becomes a free-falling object the instant it leaves your hand. Even though it's traveling upward, it's still a free-falling object. In free-falling objects, you have to assume constant acceleration if you're going to use kinematic equations. And so we're going to use the following assumptions. Acceleration of gravity, we assume that's a constant, and we're going to assume wind resistance is negligible. The first assumption is pretty good. As long as you're somewhere near the surface of the Earth, you can assume acceleration of gravity is 9.8 meters per second. If you get an appreciable distance away from the surface of the Earth, the acceleration does change. Just for your information, it's proportional to the inverse square of the distance from the center of the Earth. So what does that mean? Sea level is about 4,000 miles from the center of the Earth. You go to the top of Mount Everest, it's only an additional 5 miles. So anywhere on the surface of the Earth, you can assume acceleration is 9.8 meters per second per second. You're going to be pretty close. Now, if you're going to go hundreds of miles above the surface of the Earth, or thousands of miles, the acceleration is going to drop off. Or if you're on the surface of the moon or some other planet, then acceleration of gravity is different, of course. Wind resistance, now that particular assumption, wind resistance can be extremely significant if the object is going pretty fast or if the object is not aerodynamic. So be careful of that assumption. If an item is dropping only a few feet, it's not going very fast, and it's reasonably aerodynamic, then wind resistance is negligible. Or if you're doing an experiment in a vacuum chamber and you're dropping an object through a vacuum chamber, believe it or not, a bowling ball and a feather will be accelerated at exactly the same rate. Okay, example 3. A rock is dropped from a tall bridge. After 2.5 seconds, the rock hits the ground. And the other two are just saying, well, it's located at sea level, so we're going to assume acceleration of gravity is 9.8, and the rock is aerodynamic. All that means is we're going to assume air resistance is negligible. And why is the word dropped in red? Because that gives you a clue as to the initial velocity. And we have enough information from that to calculate the height of the bridge, darn it, and the final velocity of the rock. So again, let's draw our little picture. Notice in this case, displacement is being shown as delta y instead of delta x, because you want to be in the habit of vertical displacement, call that y. So when we get into our projectile problems, you can keep vertical and horizontal, keep them separate. So here he is, he dropped the ball off the bridge and it's about ready to hit the ground. Again, I would list your variables systematically and put down the numbers that you know. Okay, initial velocity is 0 meters per second. We know that because the ball was dropped. As the ball was released, it had no initial velocity. And then go down to acceleration. You say, okay, why is that negative 9.8 meters per second? And that's because acceleration is pulling the object downward. The direction of the acceleration is negative because we defined acceleration upward as being a positive value. This is a vector quantity, so acceleration in the downward direction would have to be negative. Time was given in the problem is 2.5 seconds. Delta y, the displacement, we can predict that that's going to be a negative number, correct? Because that particular direction from the top of the bridge to the bottom of the ground is it's going to be a negative displacement because we defined up as being positive. So let's go ahead and we have 3 variables that we know the values of 3 of the variables. We can solve the other 2. Pick any equation that has only one unknown. In this case, again, we're going to pick equation 1 and determine that final velocity is negative 24.5 meters per second. And that makes sense, doesn't it? Because the ball is being pulled downward, and we've defined negative value. We've defined downward as being the negative direction for velocity. And then we're going to plug that number in to a different equation to calculate delta y. Again, it doesn't matter which equation you use. And I've just arbitrarily picked equation 3, plugged in my numbers, and I got delta y is negative 30.6 meters. And again, not to be too repetitive, I would take my answers and plug them into equation number 2 just to check to make sure I got the right answers. Example 4. Here's a similar problem. And this time the ball is being thrown straight upward. So it's going to have an initial velocity, isn't it? In fact, it's going to have an initial positive velocity because it's being thrown in the upward direction. What the other information it's given, after 1.2 seconds, the ball reaches the highest point. Yeah, you know, when a ball is thrown upward, it gradually it slows down, slows down until it reaches its highest point, and then it comes to a stop, and then it comes back down to earth. So that highest point is a clue as to what the final velocity is. And then again, we're going to use our same assumptions. The ball is located at on sea level at planet Earth. The ball is extremely aerodynamic. In other words, wind resistance is negligible. We're going to calculate the height of the ball after 1.2 seconds. In other words, calculate the height of the ball when it reaches its highest point. And we're going to calculate the initial velocity of the ball. In other words, how hard do you have to throw that ball to get it to reach that highest point? Okay, here's another picture, a little diagram of what it is we're trying to calculate. And in this case, we call it delta y maximum because that's a maximum elevation that ball is going to reach in this particular problem. And notice it's the displacement is from the release point, not from the ground. Okay, again, we're going to list our variables. We're going to plug in the numbers that we know. We don't know initial velocity. That's something we're going to calculate. But we do know it's a positive number, don't we? Because it's being pushed upward. We know final velocity is 0 because when a ball reaches its highest point, its vertical velocity is 0. We're not dealing with any horizontal velocities in these problems. Everything is in a single dimension. Acceleration, again, it's negative 9.8 because acceleration is in these problems is the negative direction. If we define upward as being the positive direction, then acceleration is a negative number. T is given in the problem, 1.2 seconds. So again, we're gonna list our variables, we list our known quantities, we list our equations, and we go ahead and find the equation with only one unknown variable. In this case, we're going to plug into equation 1, and if you're careful with your signs, you'll determine that initial velocity in this case was a positive 11.8 meters per second. In other words, you had to throw the ball at a positive 11.8 meters per second to get it to reach that particular elevation, which we calculated as being, we plug that number in and we find out that the maximum height this ball reaches is 7.1 meters. So if you want a ball to go 7.1 meters above your release point, you have to throw it 11.8 meters per second. That has to be your initial velocity. And as you're aware, within a couple, immediately the ball starts slowing down until it finally reaches a velocity of 0. Okay, example 5. Basically, it's the same problem. We're going to throw the ball straight upward at 11 meters per second. And in example 4, we determined that if you do that, the maximum height will be 7.1 meters. Okay, so it's the same problem basically, only in this case, okay, again, we're at sea level on planet Earth. It's aerodynamic. Okay, wind resistance is 0. So in this case, what we're going to worry about is how long it takes to reach an elevation of 5 meters above the release point. And we're going to calculate the velocity when the ball reaches an elevation of 5 meters above the release point. Kind of picture somebody looking out the window and they can see the ball on its way up, and they're going to see the ball on the way down again, aren't they? So let's draw a little diagram. So here's what we're trying to solve. We know that the ball is going to reach a maximum height of 7.1 meters. On the way up, it's going to go through the elevation 5 meters, and on the way down, it's going to go through the elevation of 5 meters, isn't it? So we're going to end up with 2 different values for velocity and 2 different values of time. At least we should, because it's going to reach that elevation twice. So we're going to plug in again. I would get in the habit, list your variables, plug in the known quantities. In this case, you started at a positive 11.8 meters per second velocity. It's going against a negative acceleration. It's slowing down on the way up. Acceleration is negative 9.8 because the direction is downward. And we want to know at what time it's going to reach an elevation of positive 5 meters above the release point. So you put in a positive 5 for that value. There's your three equations. Let's plug in our numbers carefully, remembering to include our signs, very, very important. And in this case, what happens? We use equation 2, and VF squared is equal to 41.2. So that, if you solve a quadratic equation, you end up with two answers quite often. In this case, they take the square root of both sides of that equation, and you have a positive 6.4 meters per second on the way up. You have negative 6.4 meters per second on the way back down. And now if you plug in positive 6.4 into equation 1, you're going to get a time of 0.55 seconds. In other words, it takes 0.55 seconds to reach an elevation of 5 meters on the way up, and 1.86 seconds when it goes on the way down at 5 meters. So, if you end up with two answers, that's good. That's what you would expect. It's going to go through that elevation twice. Okay, final thoughts. I want you to get an A on your next physics exam, and big part of that is be extremely careful with your signs. Remember that 4 of these variables are vectors, so there's a positive and a negative direction with each one of these vectors, and you got to be very consistent, or you're going to get the wrong answer. I would say get in the habit of drawing a picture of the problem. It really helps you to visualize what it is you're solving. Especially when problems get more and more complex, it really helps to have a sketch. So just get in the habit of drawing a pretty little picture. And most teachers will give you partial credit if you put in a nice picture. Even if you get the wrong answer, at least you drew a pretty picture. Usually you'll get partial credit. At least I always gave partial credit for a pretty picture. It doesn't hurt to predict the signs on your answers. Set up your problem systematically. Always do that. List exactly the variables you know. Show your work. You'll get partial credit for showing your work. If you get the wrong answer, it doesn't hurt to write down, gee, I know this answer is wrong, but I can't find what I did wrong. Sometimes you'll get credit for that. At least having the presence of mind to say, well, I know the final velocity had to be negative. I don't know what I did wrong, but I know it's got to be negative. Teachers like to see that. They know you're thinking. I would get in the habit, usually it'll only take 2 equations to solve your problem. I would put my final answers into the equation that wasn't used and check your answers. And finally, I would be very interested in any feedback that you might have. I hope this helped. I hope you get an A on your next physics test. And I am interested in feedback. I'm going to do future sessions on like Newton's laws of motion. My intention is to try to keep them down to a half an hour or less, where I'll be solving 4 or 5 example problems that kind of demonstrate how to do the problem. And any suggestions that you would have, I'm all ears. If there's a particular topic that you would like me to cover, I'd be more than happy to. If I'm qualified to cover it, I can do electricity, things like that. I can do laws of motion, conservation of momentum, conservation of energy, those kind of sessions I intend to do. So anyway, I hope this helped, and thank you for your attention.